Hi, I'm going to make one more video on section 7.3. That's the exponential random variable. I should have shut my door because I got home washing clothes. I was really scared. I turned on my laptop and it sounded like a buzz saw. It finally quieted down, but I'm not really sure. So if you start hearing something like I'm chopping wood, it's my computer. Anyway, we were talking about the exponential random variable. Remember, for the exponential f of x, the density function is lambda e to the negative lambda x for x is greater than 0. And so this statement is somewhat true. Time intervals between consecutively occurring events are frequently modeled by an exponential random variable with parameter lambda. I should say when events occur according to a Poisson process, the time between those events is exponential. So let me show you how we derive that. Let x be the number of accidents in 1 week in a certain city. We can say x can be modeled by a Poisson random variable with a parameter lambda, so there's lambda accidents per week. X is definitely discrete because you're counting the number of accidents in a week. So the probability mass function of x, you're counting number of accidents, is e to the negative lambda, lambda to the x over x factorial. This, of course, is the mass function for Poisson. Let's let t be the amount of time that passes between events or until the first accident. Anyway, here, let's say this is a Poisson process, right? And here's maybe 1 week time. And then next is another week. So this is time 0, 1. This is the first week, and then we would have the second week. But I'm going to count how many accidents are in this week. And let's just say, they occur according to a Poisson process. Maybe lambda is 3. We can expect about 3 per week, maybe 4. But what I'm trying to measure now is the time between events. So these little intervals are times between things occurring. So maybe we'll call this T1 or T2 or T3. I'd like to figure out how much time occurred between accident 2 and accident 3. And amazingly, that's going to be modeled by an exponential random variable. So here's how we set that up. Let's start at time equals 0 and let capital T be the amount of time that passes until the first accident. So T is continuous because we're talking about time between accidents. So if we let t weeks pass until the first accident, that means there were no accidents in the first t weeks. So we're kind of playing a little game now. And in t weeks, we'd expect there to be lambda t accidents. So if there's 3 accidents per week, then there should be 3 t accidents per t weeks. So the probability there are no accidents in the first 0 to t weeks would mean in the in the Poisson, we're going to let x be 0, meaning no accidents occurred, where they should occur at a rate of lambda t. So this is what we get. The probability there's no accidents in the interval 0 to t is e to the negative lambda t. But if you remember from the last video, this is just the survivor function of an exponential random variable, and the survivor function tells you the time between accidents. So time after, what's probably the time after the first accident happens is at least t weeks, or the time until the first accident happens is at least t weeks. So now we've kind of related the survivor function of an exponential with the Poisson random variable. So again, if you take the CDF of this is just 1 minus, and then if we take the derivative, we get f of t. So what we're showing is if t is an exponential random variable with parameter lambda, then that's the time between accidents. So that's probably no accidents occur in the interval 0 t is the same thing. The probability that the time it takes for the first accident is bigger than t. So yeah, I'm sorry if I'm not saying this perfectly, but maybe an example will help. This is a hard concept, but the nice thing is it allows us to do some problems if you see it in a discrete manner. How many accidents? You could do it that way, or if you want to look at it time between accidents, you can go back and forth, and I think that it's kind of cool. So there's the fact I was just saying, and let's just do this one here. I think maybe if I can do one. Suppose that calls occur at the homework hotline according to a Poisson process, 4 calls per hour. So if there's 4 calls per hour, that means there's 15 minutes between calls. Okay, so determine the probability that more than 2 hours pass between calls. So I'm going to let X be the number of calls per hour, and we said that's lambda with 4 calls per hour. And I'll let Y be the number of calls that occur per 2 hours, because what we're looking at is the probability that we receive no calls in 2 hours. So if Y is number of calls per 2 hours, then Y is Poisson with lambda equals 8. So the problem's asking what's the probability at least 2 hours elapsed between calls. That means there were no calls in 2 hours. That means Y, which measures how many calls there are in 2 hours, is 0. And this is how I would set it up as a Poisson. That's e to the negative 8, because this is lambda. Lambda to the 0, no calls over 0 factorial. Now, we could have done this as an exponential. So determine the probability that more than 2 hours elapsed between calls. So more than 2 hours, I'm switching to minutes, that's more than 120 minutes. So if t is the time between calls, there's 15 minutes between calls because we said 4 occur per hour. So if on average there's 15 minutes between calls, then t is exponential, and this is the mean, so the parameter is 1 over 15. So I'm solving probability t bigger than 120 with an exponential of a parameter of 1 over 15. I'm using the survivor function here, and I get the same value as I would down here. So it allows me to think that I can either say, what's the probability that no calls come in a 2-hour period, which is the same thing as saying the time between calls is more than 120 minutes. So there's that nice relationship. And this is a tough idea. So if you'd like to make another video, talk slower, start with examples straight out, just send me an email and let me know. And hopefully my computer will still be living. Okay, bye.